Haloalkanes then is the general name for saturated organic compounds containing halogen atoms. You can also get haloalkenes and stuff, and the property of the halogen is similar in those as well, but we'll just focus on these for the moment. So the first thing you need to be able to do is to name them, and that's very straightforward because you just apply the rules you already know. So if we take a simple example like that, you would just say, right, it's got a chain of 5 carbons, so it's pent. It's saturated, no carbon-carbon double bonds, so it's ane. But it's got a chlorine attached to it, and the way you deal with that is by putting chloro in front of the name. So make sure it's chloro, not chlorine or anything like that. It's got to be chloro or iodo or fluoro or whatever. And you need a number to indicate where it is. So in this case it's going to be 1, 2, 3, so 3 chloro pentane. So naming shouldn't be a big deal. The second thing that we need to think about is what effect does it have on the physical properties, by which I mean melting point, boiling point, solubility and water. What effect does it have putting a halogen atom into the molecule? So if we compare two very similar compounds, so we've got ethane and we've got fluoromethane. Okay, so those are similar in the sense that they're a very similar size. You can see actually the total number of electrons in the molecule is the same for both. So you've got, because you've got 6 for the carbon and 3 for the hydrogens, which takes you to 9, which is the same as the 9 in the fluorine. So those are molecules that are directly comparable in terms of the numbers of electrons. And if we compare the boiling point of ethane is minus 89 degrees C, and the boiling point of this is minus 78 degrees C. So it's not a huge difference, but you can see that even though we're comparing very similar molecules, putting the halogen in increases the boiling point. Okay, minus 78 is a higher temperature than minus 89. And that, of course, is because it makes the molecule polar, whereas these molecules are non-polar. Okay, so ethane is a non-polar molecule, and therefore only induced dipole-dipole forces have to be broken when it boils. Hopefully you're getting very used to these boiling point issues now, because we practiced that a lot last term and they keep coming up again this term as well. So that's what we would say for hydrocarbons, that they're essentially non-polar because carbon and hydrogen have very similar electronegativity. They're essentially non-polar molecules, and therefore all that happens when you melt them or then vaporize them is that you break these induced dipole-dipole forces that all molecules have between one molecule and another. However, the halogens are all more electronegative than carbon, fluorine especially so. And so when you have a carbon to fluorine bond, it will have a polarity like this. Okay, because fluorine's more electronegative, meaning it attracts the bonding electrons more strongly, and that's a very important word, electronegativity. It means that that electron pair is pulled more towards the fluorine than the carbon, so you get a delta minus charge and a delta plus charge, meaning more of the electron densities on the fluorine. So this is a polar molecule, and that means that you get not just induced dipole-dipole forces, but also permanent dipole-dipole forces. Permanent because that dipole is there all the time. So you get induced and permanent dipole-dipole forces. And those have to be broken, so I won't write all that out again, but you get the point that they too have to break when it vaporizes. And generally speaking, the permanent ones tend to be stronger than induced ones, which makes intuitive sense. If the dipole's there all the time, it's likely to be harder to break than if it's only there, now and again as a result of the random electron movements. So permanent dipoles tends to mean that you've got a stronger attraction between the molecules, so more energy is needed to break the bonds. Or to break these intermolecular forces. And if more energy is needed to break them, you get a higher melting point or boiling point, or a lower volatility. Okay, so if you're not yet comfortable with these kind of comparisons of melting and boiling points, that's a bit of a priority, because we've done it quite a lot, and I think it would be a good time now to really nail it down and make sure you can do that and explain things like why this has a higher boiling point than that. It's important that you don't think that because you have a permanent dipole in a haloalkane that the induced dipole-dipole forces don't matter. And you can see that if you compare a series of compounds like this, they all have a permanent dipole because the chlorine is more electronegative than the carbon, but they don't all have the same boiling point. Okay, the boiling point increases as you increase the length of the chain. And that's because in addition to the permanent dipole-dipole forces that are associated with that bond, you still have induced dipole-dipole forces, and as you increase the size of the molecule, you increase the surface area in contact with other molecules, and therefore you increase the number of induced dipole-dipole forces that have to be broken. Hence, more energy is needed and the boiling point increases. So don't ignore the induced dipole-dipole forces just because there are other things as well. Okay, so that's due to increasing surface area in contact with other molecules. So more induced dipole-dipole forces need to be broken. And so on. I won't write the whole lot out again, but you get the idea. So more of those need to be broken, so the energy required is greater, and therefore the boiling point is bigger, or the melting point is bigger, or whatever. So that's important. Now when it comes to solubility in water, the important thing to remember is that organic compounds will generally not be soluble in water unless they can provide something that's reasonably competitive with the hydrogen bonds that water molecules would otherwise form to each other. And that means that the organic compound needs either to be able to form hydrogen bonds itself, or it needs to be ionic, and we will later in the course come across some organic compounds that include ionic groups. But here, there is nothing that can form hydrogen bonds in simple haloalkanes like this, so you would say that these are insoluble in water because they can't form hydrogen bonds to water. Okay, so if you're asked for the explanation, that's what you need to say, insoluble because they can't form hydrogen bonds to water.